Hello and good day. Today I'm going to show you how to conduct a between groups ANOVA F-test in Excel. Now we conduct F-tests when we have more than two groups in our particular research study. So when we talk about groups, we're talking about the levels of the independent variable. And so if I only had two, I would just do a t-test. But if I have more than two, then I can't use a t-test, and you learned about that in the narrated PowerPoint. When we have more than two levels of an independent variable or more than two samples, then of course we could do several separate t-tests, but the problem with that is that we would inflate our alpha by a magnitude of the number of statistical t-tests that we did. So the solution is to do an ANOVA F-test. And that way we measure all the samples in comparison to each other simultaneously at the same time. So what we call an omnibus test. And what you also learned in Module 4 is the difference between a between groups and a within groups design. And so the between groups ANOVA is an independent samples test, similar to the independent sample t-test. It's so similar, in fact, that all the assumptions are exactly the same as they were in the last module. So that should make it a little bit easier when it comes to remembering and determining if you're meeting your assumptions. So just as a reminder, in an independent design or a between groups design, each observation is measured once and only once and is in one and only one of the samples or groups. So again, because each observation is in only one of the groups, assignment becomes important. And so remember in the last module, we talked about the difference between assignment and selection. Assignment is when we determine the observations in a sample and which level of the independent variable they're going to be measured in. So remember, in a random assignment, each observation in our sample is assigned in a random fashion, usually by the use of a statistical package or a random number table. With a convenient assignment, no random process is in place. So maybe the researcher decides which group each participant is going to be in. Maybe the participants decide themselves, or maybe there's an individual difference that we use to determine who's in which group, something like personality. So if you're high on extroversion or low on extroversion, you might be placed in different groups. That's an individual difference. How social you are cannot be randomly assigned because you come as you are. Now with the ANOVA F-test, we're going to use a new distribution. It is the F distribution. You will remember that that distribution is a skewed distribution. It starts at 0 and it goes for infinity only in the positive direction. So there's a positive skew to it. Now this distribution, although it's positively skewed, is based off of the t distribution. So if we were to take the t distribution and square all of the values in the t distribution, if we were to square all the numbers in a t distribution, all the negative values would become positive, and all the larger values or more extreme values in either direction, positive or negative, would become even more extreme. So that would skew our distribution. So the F distribution is a unimodal distribution, but it's a skewed distribution. It is not a normal distribution. And it becomes skewed because we're squaring the t statistic values. So that means the F distribution in its most basic form with two samples is just simply t squared. So if I take a t statistic squared, I'm going to get an F statistic. If I take the square root of F, I'm going to get a t statistic. So make sure you know the relationship between t and F. Now, because we have multiple samples, that means we're going to have multiple comparisons. So if we reject the null hypothesis, and only when we reject the null hypothesis, we'll have to continue and do what's called post hoc tests. So today in Excel, I'm going to show you how to do the F-test itself. And then when we reject the null hypothesis, I'll show you how to do Q-tests, which are post hoc tests. Now, if we fail to reject the null hypothesis with our hypothesis test, we do not need to do post hoc tests, because remember, when we fail to reject the null hypothesis, we're saying there's no differences among our groups. So if there's no differences among our groups, then there's no reason for us to go looking for differences that are not there. So let's go ahead and jump into an example. Let's do that F-test and let's do some post hoc tests so you get a feel of what it's like to do a hypothesis test in ANOVA from start to finish. As always, make sure you open up your Excel spreadsheet below and also the directions. Hopefully you have that spreadsheet open. Let's go and take a look at our variables that we have here. Looks like we have 3 columns of data. We have what looks like to be negative outlook. So neg out is negative outlook. New out is neutral outlook. Pos out is positive outlook. So let's go take a look at the code book. Let's get a better feel for our data here. So you're going to see our 3 variables here. And so in this case, negative outlook is how likely are you to care physically, financially, and emotionally for your parents when they're no longer able to care for themselves when you have a negative outlook on life. The second sample that we have is how likely are you to care physically, financially, and emotionally for your parents when they're no longer able to care for themselves when you have a neutral outlook on life. Then finally, it's the same question, your likelihood to care, except now when you have a positive outlook on life. And so notice here that our independent variable is your outlook on life. It has 3 levels or 3 groupings. It could be negative, it could be neutral, or it could be positive. The dependent variable here is going to be how likely you are to care for your parents. And so again, separate the independent from the dependent variable. The dependent variable is what we're interested in measuring. We want to know likelihood of caring for parents. That's the dependent variable. The independent variable is the grouping variable. It's the nominal variable, in this case, either being negative, positive, or neutral when it comes to your outlook on life. So let's look at our scenario here. Let's make sure we understand what's going on. Remember, statistics always happens within a context. So it looks like in this scenario that decisions about long-term care for elderly populations affect most families as relatives age. So suppose you're interested in knowing the factors that may predict whether a person chooses to care for a parent once they're no longer able to care for themselves. So you suspect that a person's general outlook on life, positivity, is one of those factors. You decide to ask college students 2 questions. So one question asks about their outlook on life as either being negative, neutral, or positive. That is your independent variable. The other question asks about their likelihood of caring for their parents when their parents are no longer able to care for themselves. That is your dependent variable in this particular scenario. Remember, the dependent variable is what's being measured. The independent variable is their grouping variable. So we'll use our data in Excel here, and we're going to use an alpha of 0.01 for this hypothesis test. So again, an alpha of 0.01 is a 1% chance for a type 1 error. So in other words, if we reject a null, if we say your outlook on life matters to you caring for your parents, then there's a 1% chance that we are going to be wrong. So that is our scenario. I'm going to go back to our data view here, and you'll see each of those categories: negative outlook, neutral, and positive. The numbers underneath each of these headers represents the likelihood for caring for one's parents when they're no longer able to care for themselves. And you'll see here, if you hover over the label, you'll see what that scale looks like. So 1 on the scale is very unlikely, 7 is very likely. So the higher the number, the more likelihood you are to care for your parents in their older age. You will note also that we don't have equal sample sizes, and that's perfectly okay because we have a between groups design here. It's an independent groups design. So any one of these observations is not related to any other observation that's in our data set. And so if we have more values in one of our groups than the others, that's perfectly okay. If you're looking at the counts of these values, you'll notice that none of these groups reach 30. So it doesn't look like we can assume normal distributions in our analysis here, but that's okay as long as we note the limitation and know what that limitation tells us. In this case, not being able to meet that assumption suggests that our results of our study may not be valid, but realize that we are averaging over observations here. And so it's more likely to be a normal distribution than not. We're just not confident. So it's not like our results are worthless. It's just we're just a little bit more skeptical and cautious about the results when trying to say that there is some causal inference going on amongst our variables. So now that we know a little bit about our data set, let's go ahead and go to our directions document. You'll notice that there are several steps to conducting a between groups ANOVA. It actually goes pretty fast. We don't have to do a whole lot of data manipulation here. So you're going to notice that step 1 is getting our descriptive statistics. We know how to do that. And step 2 is conducting ANOVA analysis. And we'll walk through that here in a second. But first, let's go ahead and get our descriptive statistics. We're going to get it for each one of our groups or each one of our samples. So as we've been doing all semester, go up to data, data analysis, descriptive statistics. We'll click OK. We'll put in our input range, click our labels box, our summary statistics, and then we'll put our output a few columns away from our data. I'll put it in F2 here. We don't need to check the confidence level box. We can if we want, but we're not going to use it here today. And we'll click OK. We'll do that for the other 2 groups as well. Again, just change your column, change your output location. And then we got one more. Okay, and there's our three groups. If we're to just kind of glance at the means really quick, we see that the mean when it comes to caring for one's parents, when you have a negative outlook, is about 5.17. When we have a neutral outlook, it looks like it's about 6.68. And then with a positive outlook, it looks like it's about a 6.53. So slightly less than the neutral outlook. Now, of course, we see some mean differences, but it doesn't necessarily mean that they're statistically different at a greater than chance level. That's why we do the F-test. That's also why we do the follow-up post-hoc test to make some distinctions between each of the groups. You will notice if you're looking at the skewness statistic for each one, it looks like there's a negative skew. But remember, that's at the individual observation level. That's not at the group level, not at the sample level. Remember, when we average over observations, we bring the tail of the distribution closer to the normal distribution, so we bring that tail in. And so even though we show some negative skew here, realize that that's being minimized by the fact that we're averaging over multiple observations. So in one case, we're averaging over 18, another one is 28, another one is 17. So even though we can't be confident all three are normal distributions, the fact that we're averaging over observations makes us more confident that it's going to be more normal than skewed. But it's still a limitation at this particular study. All right, so we have our descriptive statistics. Let's go ahead and start our ANOVA process. We're going to go data analysis. We're going to select ANOVA, in this case, single factor. So one independent variable. Remember, independent variables have multiple levels. We'll click OK. We'll highlight our data. We'll make sure that we're selecting by our columns. Then we're going to click labels in the first row. We'll verify our alpha and verify our location for the output. So let's do it. We're going to go data analysis, and you'll notice at the top we have three ANOVAs. The one that we want is the single factor ANOVA. And click OK. And notice that we're just going to highlight the data that we want. I'm just going to select our three columns, so A, B, and C. And we'll gather all the data that's there in all three of those columns. We do have labels in that very first row, right? That's that row number 1 here, negative outlook, neutral, and positive outlook. If we did not have those labels and just had data, we would not check that box. We're going to check our alpha here. In this case, we set an alpha of 0.01, so we're going to change that to 0.01. And then we're just going to select someplace in our spreadsheet to place our output. I'll put it right next to our descriptives, and I'll click OK. Right, so now that we have our output, you're going to notice a few things. You're going to notice that we're going to have our summary box right here. In this summary box is going to give us our counts. So how many observations in each one of our groups or each one of our samples. You're also going to see that we have the averages, and we just went through those averages when we got our descriptive statistics. Now, the whole reason why we got our descriptive statistics is so that we have more information there in case we need it, but also so we can get that standard deviation for each of our groups. So that way we have it for when we want to report it. Then our third column is variance. And then remember that variance is just the standard deviation squared. So if I didn't get my three descriptives, I could create another column here for my standard deviation. And all I would have to do is take the square root of each of my variances. Take it to the power of 0.5. And I would have my standard deviation. So notice that this standard deviation here matches the standard deviation that's in my descriptives. So again, you don't necessarily have to get your descriptives. I find it easier because we've been doing it all semester long. But if you remember that the standard deviation is just the square root of the variance, then you could go straight to your ANOVA output and just calculate those standard deviations on your own and not have to get your descriptive statistics. All right, so that's the summary box. Let's go down to the ANOVA box. This is the one we're particularly interested in because this is where our hypothesis test is. You're going to notice that we're going to use what's called a source table. Now, some students find source tables easier to use, especially if they're hand calculating. But again, right, we don't do hand calculations a whole lot anymore, right? We use statistical packages. We use computers to do it for us. But you're going to see several sources of variation. We're going to have our between groups variation. So that's the variation or differences between our group means. Remember, our means differ, they vary. That's our variation. We're also going to have our within groups variation. Essentially, that within groups variation is telling us that the values within each of our groups differ or they vary. And you see that, right? We have 7s, we have 1s, we have 4s, we have 3s, right? And they differ within each of the groups. So that's our within groups variation. And then finally, we have our total amount of variation. So in this case, it's how all the numbers differ from each other. So within groups is within each of the groups. Total is across all the values that we have. And we see those values differ. So that's where we're getting these sources of variation. You'll see that we have our sum of squares there. That's just the numerator that you would see in a variance formula. If you remember from the very last module, module 4, you'll remember variance was s squared. And to get that variance, you took each value and you subtracted the mean of the sample, squared, summed it together, and then divided by n minus 1. Well, all that really is the sum of squares, which is the numerator, divided by what's called the degrees of freedom. And we talked about degrees of freedom in the last module as well, and that's the denominator. So even though this looks different, we've seen these concepts before. The sum of squares is simply the sum of the squared deviations from the mean. The degrees of freedom, or the DF column in your source table, is simply the degrees of freedom. And so you'll notice that we have 3 different sums of squares, and we have 3 different degrees of freedom. And so I'll talk a little bit about those as we go through this table. Now, something to note that I see where students get confused quite a bit is in the terminology of between groups and within groups as sources of variation versus between groups ANOVA and within groups ANOVA. And that can be confusing because they're 2 separate things, but yet they use the same terminology. So when we talk about between groups variation, what we're talking about is the differences in the values within our data set. The same thing when it comes with our within groups, it's within the data set itself. And when we talk about a between groups design, what we're saying is that our samples are independent of each other. And with a within groups ANOVA, we're saying our samples are dependent on each other. And so those are 2 separate things. So you'll find that when we do a within groups ANOVA, that we're still going to have between groups, within groups, and total variation. So variation is different than the ANOVA design. So those are 2 separate concepts. It's easy to confuse because you see the between groups and within groups for both of them, but they're 2 separate things. One has to do with variation, the other one has to do with the ANOVA design. All right, so let's talk about each of these sums of squares in this very first column in the source table. Each of these sources of variation for the sum of squares will be a variation of the variance formula that we learned in the last module. So for my between groups source of variation, the formula we use is SS for sum of squares. We'll do a subscript between, or BT, equals the mean of each of our groups. I'll call the first one X, minus the overall mean of all the values in our data set, squared, and then multiplied by the sample size of that group X, or the very first group. So notice that becomes a sum of squares to get squared values, and then we multiply it by the number of observations within that particular group. We would then add that for our sum of squares of the next group, so the mean for next group Y minus the grand mean squared, and again multiplied by the sample size for Y. Then we would add one more. So for our third group, it would be the mean of the third group. We might call it Z, minus the grand mean, or the overall mean across all of our data points, squared, and multiplied by the sample size for that group as well, for Z. And that's how we get the sum of squares between each of our groups. So essentially what we're saying is that the means differ between the groups, and this is how much they differ in terms of squared values. Now mathematically, for our within group sum of squares, our formula is sum of squares, subscript WI for within, equals each value within the group. So all my values in my first group, which I might call X, subtracted from the mean of the group. So the mean for X. We would square all of those deviations, and then we would sum them up. So again, sum of squares. And then we would add the values of the next group minus its mean for the second group, squared, summed up, sum of squares. Plus our third group, we'll call it Z, minus the mean for Z, squared, summed up. So notice here that the computer is going to do all this calculation for you, but just so you know where these values are coming from, they're coming from our original data, and it's within each of the groups. So each x value, or the first values in our first group, minus the mean of that group, squared, summed together, plus each value in the next group, minus its mean, squared, summed together, plus all the values in that third group, minus its mean, squared, summed together, and that's going to give you this within groups sums of squares. And so here we get 60.84. Now finally, mathematically, for our last one, the sum of squares for total, the formula is SS for sum of squares, but we'll subscript it as TOT for total. And it's going to equal each value in each of our groups minus the grand mean squared summed together. So we take every value in that first group, we subtract the grand mean, square it, sum it together, plus each value in the next group, minus the grand mean, squared, sum together, plus, you might guess it, every value in that third group or that last group, minus the grand mean, squared, sum together. And that would give us our sum of squares total. In this case, we get 88.32. Now again, I'm not asking you to do those calculations. You can if you wanted to check the source table to see exactly how it's done. But I'm more interested in that you're able to get the output and that you know conceptually what is happening for you to get that output. Now, once we have our sums of squares, we then need to get our degrees of freedom, because remember, our whole goal is to get our variances. So the F-test is an analysis of variance. So I need variance. So in this case, our mean squared, this column right here, is simply going to be the sum of squares divided by the degrees of freedom. And remember, that is just our formula for variance. So before we said that S squared for variance was simply the sum of squares divided by the degrees of freedom. So it's the same idea, except now we have 3 sources of variation. Therefore, we have up to 3 sources for variance. And so that's what this third column is going to calculate. Now, mathematically, it's really simple. We have our sums of squares. So we're just going to divide across the rows. And that's going to give us our mean squares. So that means I would take 27.475, divide by 2, and that would give me 13.74. Same thing with our within groups. We would take 60.84, divide by 60, and that would give me 1.01. And so my mean squared values for between groups and within groups would just be my variance between the group means over the variance within all of the groups. Now to get the F statistic, we would take the variance between the groups, or MS between, and divide by the variance within, or MS within. And so we saw that in the narrated PowerPoint already. And so notice that Excel does that for you. That's this F value right here. In this case, that F value is 13.55. Now that F statistic by itself doesn't mean a whole lot unless you have a critical value. So notice there's going to be a critical value in your output as well. In this case, that F critical is 4.98. So if I'm drawing out my F distribution, it's always a positive distribution. We'll put in our critical region in the tail. So at an alpha of 0.01, or 1% chance for an error, it looks like that F critical value, so F crit, is 4.98. If I exceed that value, we are going to reject the null hypothesis. If we do not exceed that value and we get a value between 0 and 4.98, we will fail to reject the null hypothesis. In this case, we got 13.55. That's definitely someplace way out here. It looks like we're going to reject the null hypothesis. And so what that tells us is that there is at least one difference among our groups for our hypothesis test here. Now, we don't know where that difference is. It could be between negative and neutral outlook. It could be between neutral and positive outlook. It could be between negative and positive outlook. We don't know. We know we have 3 comparisons here. We know that at least one of them is significantly different at a greater than chance level. So there could be 2 that are different, it could be 3 that are different. We don't know until we do what's called post hoc tests. So we'll do post hoc tests in a minute here, but first we're going to get our effect size. But just remember here at the group level, it appears that we find that there are differences in how likely someone is to care for their parents depending on their general outlook on life. Remember, this is real data. These are coming from students, so this isn't made up data. It looks like there is something to how likely someone will care for their parents based on their outlook on life or their positivity. All right, so let's go back to our directions here really quick. Now, we already got our F statistic, and so notice here it's just reminding you that if your F statistic is greater than your F critical, we're going to reject the null hypothesis. Null hypothesis being here that there is no difference among our levels of our independent variable for our dependent variable. Now, our research hypothesis would be there's at least one difference, and that's very important wording. So when you're writing out your null and research hypothesis for an F-test, make sure that you state for that research hypothesis that there is at least one, could be more, but there's at least one difference. If you just say there is a difference, then all you're saying is that there's one difference, but there could be more than one. So we want to make sure we say there's at least one difference, and that's a critical wording change when it comes to your null and research hypothesis. What's nice about the F-test, you don't have to worry about wording it for a 1 or 2-tailed test. Remember, we're squaring all the t statistic values, so we're only going to end up with a 1-tailed skewed distribution anyway, so you don't need to worry about negative and positive tails or anything like that. All right, so now let's look at our effect size. So remember the reason why we get the effect size, and this is really important that you verbalize this in your explanations for the practical decision. Also, when you explain your effect size, that the effect size is at the individual level, not the group level. The hypothesis test is at the group level, so we're looking at multiple observations averaged over each other. The effect size is at the individual level. So what would this mean for my parents? What would this mean for your parents as individuals, not as a group? So overall, positivity may matter at the group level for human beings as a society, but maybe it doesn't matter for the individual, and that's what this effect size gives us. So you notice that our calculation for the effect size is going to be a lot easier than it was in our previous modules. The effect size symbol is r squared. We call this the coefficient of determination. And it's simply our sum of squares between, so from our source table, the sum of squares between divided by the sum of squares total. So that'll be really easy to calculate. I'll show you how to do that here in a second. Now note our conventions for the effect size have changed. So remember when it was a t-test, if we had an effect size around 0 is no effect, there's around 0.2 we had a small, 0.5 is medium, 0.8 was large. But here, notice that the values are quite a bit smaller, and that's because we're squaring all of our values within our calculations. So when you square decimals, the values get smaller, not larger. So you notice here that a 0 is a no effect, around 0.01 is a small effect, around 0.06 is a medium effect, and around 0.14 is a large effect. What's nice about the coefficient of determination is that it's a ratio. So if it's a ratio, we can talk about it in terms of percent. So the r squared or the effect size calculation is quite simply the percent of the variation in the dependent variable that is accounted for by the independent variable. And we'll talk about an example of that here in a second as well. So let's go ahead and let's get that effect size calculation. I'm just going to scroll down here to below my source table. I'm just going to type in effect size. I'll go to the cell that's next to it. So remember that formula is simply the sum of squares between divided by the sum of squares total. So I'm going to hit equals. I'm going to click on my cell for sum of squares between. In this case, it looks like it's 27.48. I'll do my / for divide, and I'm just going to click on the cell for the sum of squares total. Looks like it's 88.32, and I'm going to hit enter. It looks like I get a value of 0.31. So looking at my effect size conventions, 0.31 looks like it's definitely going to be a large effect. So again, go to the one that's closest to, and so in this case, given our 4 values here, it's going to be much closer to 0.14 than to any other value for our convention. So this looks like it's going to be a large effect. Now that means that this looks like it's going to impact the individual as well as the group. So remember the hypothesis test, the F-test told us at the group level that appears that outlook matters when it comes to caring for one's parents. The effect size is telling us at the individual level, what does this mean for an individual such as myself or such as you? And it looks like on average, we would expect that someone's outlook on life is going to affect how likely they are to care for their parents. And so that's what the effect size is telling us. Now, if you were to write this out, we would say that 31% of the variation or differences and the likelihood of caring for one's parents can be accounted for by the individual's outlook on life. Remember, it is a ratio. We can turn that into a percent just by multiplying by 100. So 0.31 becomes 31%. So in more simplistic terms, what we're saying is that if we were to look at our original data here, that we would see that all these values differ. We have 3s, we have 4s, we have 7s, we have 6s. They all differ from each other in some way. And that 31% of the reason why they differ is because of the individual's outlook on life. So we find in our particular study right here that outlook on life matters at the group level as well as the individual level when it comes to caring for one's parents as they get older. All right, so that's our effect size. Now notice that we don't have to worry about confidence intervals here when it comes to our comparisons, but we need to do what's called a post hoc test. So let's go back, look at our directions here. And so this next part is talking about calculating our post hoc tests. So again, we said the F-test told us that there is at least one difference among our comparisons, but it doesn't tell us where that difference is. So remember, we have negative outlook versus neutral. We have negative outlook versus a positive outlook, and we have a neutral outlook versus a positive outlook. The F-test told us that among those three comparisons, at least one of them is significant at a greater than chance level, but it didn't tell us which one. So the post hoc tests are going to tell us, again, post hoc meaning after the fact. So after the fact of our F-test, where are the differences between each of our groups when it comes to caring for one's parents? So the formula for the post hoc test, by the way, it's called a Q test. So I'll scroll down to the Q statistic here really quick. So in this, you'll see that in this formula, we're going to take the means of two groups at a time, and we're going to divide by a pooled standard error. And you've seen this formula before. It's quite simply the T statistic formula. Now, what makes it different, what makes it a Q statistic rather than a T statistic, is the denominator. So in the denominator, the standard error in a t-test is only for two groups. But in a q-test, the standard error is for all groups, not just the two that you're comparing. And so that's what makes it different than the t-test. So make a note that the difference between a t and a q-test has to do with that denominator, has to do with that standard error. And a t-test, that standard error is only for two groups. For a q-test, that standard error is for all the groups in your particular study. So the numerator is just the mean subtracted from each other. We have those already, so that won't take any effort for us to get for our calculations. But we do need to know how to get that standard error pooled. And so you'll see that formula just right above. So SM equals the mean squared within divided by what's called the harmonic mean. So we need to calculate what's called a harmonic mean. And of course, we take the square root. So that mean squared within is in your source table. We'll need to calculate that harmonic mean. But luckily, we have a formula for that. If you scroll up, you'll see that harmonic mean is going to be K, where K is the number of groups you have in your data set. In this case, we have three, right? We have neutral, we have negative, we have positive outlook. Those are our three groups. And we're going to divide 1 over the sample size of each of those groups. So we'll do this calculation first to get our harmonic mean. Then we'll plug that harmonic mean into our standard error pooled formula. And then we'll use that standard error to calculate each of our Q statistics for each of our comparisons. So essentially, we're doing three separate comparisons, just like we would with a t-test, except we're going to control for alpha inflation. And so you remember from the narrated PowerPoint, we talked about alpha inflation. Okay, so let's go back to our spreadsheet. I'm just going to go right below my effect size. I'm going to type in post hocs. Now we have three comparisons. We have negative outlook versus neutral outlook. We have negative outlook versus positive outlook. And then finally, we have the neutral outlook versus the positive outlook. So those are going to be our three comparisons. And we're going to get a Q statistic for each of those comparisons. But before we get that Q statistic, we need to get two things. We need to get our harmonic mean, and we need to get our standard error pool. So first we'll start with the harmonic mean. So if you're looking at your directions document, that harmonic mean again is going to be K, the number of groups. Here we have 3 groups. If we had 5 groups, we put 5 in there. Here we only have 3. And we divide by 1 over the sample size for each of those groups. So let's go ahead and do that. So I'm going to go to the cell right next to my symbol for harmonic mean. I'm going to click in equals. I have 3 groups, so I'll type in 3. I'll put in my divide sign. I'm going to open parentheses. And it's really important that you open parentheses here because we're going to do 3 divisions and addition among those divisions. So we want to make sure that we go in the order of operations here. And so remember, for that formula, it's going to be 1 over the sample size of my first group. And if you go up to your summary table, you'll see that count. It's 18, so it's 1 over 18. And then I'm going to hit my addition sign, so plus 1 over or divided into 28 for my second group, plus 1 over the sample size of my third group, which is 17. And then I'm going to close my parentheses and hit enter. And that's going to give me my harmonic mean. Now the harmonic mean is just simply the weighted sample size across all of our groups. So your harmonic mean should fall someplace between your lower value and your higher value for your count. If you get something outside that, so if you get something outside of 17 and 28, then you've done something wrong with your harmonic mean. Here we get 19.99. That does fall within that range. And so it looks like we're okay here for when it comes to that calculation. Once we have that harmonic mean, remember now we need to calculate that standard error pool. To get that standard error, we're going to take the mean squared within from our source table, and we're going to divide by that harmonic mean that we just calculated. Once we divide, we're going to take the square root of that division. So I'm going to go back to our spreadsheet, click on that cell that's right next to my symbol for the standard error pooled. I'm going to hit equals, and I'm going to do my open parentheses again, except this time I'm going to take my mean squared within. So I'm going to go to my source table. My mean squared within is going to be this value of 1.01. And I'm going to divide by that harmonic mean that we just calculated, 19.99. I'll close parentheses, and I want to take the square root, so that means I'm going to take it to the power of 0.5. I'm going to get that little caret symbol or that arrow symbol and type in 0.5. Okay, and that's going to give me my standard error pool. It looks like we get 0.23 if we round it 2 places. And so that's going to be the denominator in each of my calculations for the Q statistic. So let's take a look at our directions. Let's go down to that Q statistic formula. So notice here with our Q statistic, we're going to take the mean of each of our groups in the comparison. So 2 at a time, 2 groups at a time. And then we're going to divide by that standard error pool that we just calculated. So I'll go to my spreadsheet here. We're going to get each of our Q statistics. So I'm going to take negative versus neutral. So I'm going to hit equals, open parentheses. I'm going to go up to my means. I'll take the mean for the negative output. I'll subtract the mean for the neutral outlook. Close parentheses. And now divide by that standard error pool or that 0.225 number. Hit enter, and there's my first Q statistic. So when I compare a negative outlook versus a neutral outlook, I get a Q statistic of negative 6.71. I'll do the same thing for negative versus positive. So open parentheses. I'll click on my average for the negative minus the average for positive. Close parentheses. Divide by that standard error pooled. It looks like I get negative 6.05. So I got one more comparison between the neutral and positive group. So I'll hit equals. Mean for the neutral, 6.68, minus the mean for the positive, 6.53. Close parentheses, divide by the standard error, and hit enter. And it looks like we get the value of 0.66. Okay, so there's all of my test statistics for the Q-test for the post hoc tests for comparing negative to neutral, negative to positive, and neutral to positive. Now, the only problem is that I have Q statistics, but it doesn't tell me a whole lot until I have a critical value. So now we need to get a Q critical value. Every single one of our hypothesis test statistics is always compared to a critical value that's based on chance. So what we want to know is, are these differences between these groups greater than chance? Well, the only way we're going to know that is if we compare to a critical value. So I'm going to pull up our table. Again, this is located in the back of your book or on one of the files on the course website. I'm going to go down to table B5, and this is going to be on the appendix page B8. And you're going to notice that it says the Q statistic or Tukey's HSD test. That's the one that we are doing here. So this is our post hoc test. And you're going to notice that we have several columns and we have some rows here. The very first column that we see is going to be for the number of treatment levels. This is your independent variable levels. In this case, we have 3. We have 3 levels. We have negative, neutral, and positive. So make sure you know your independent variable and you know how many levels you have. In this case, we have 3. The next thing we need to know is our within groups degrees of freedom. Now we have that. That is in our source table output. So if we go back to our spreadsheet, you're going to find our degrees of freedom within right here. It's going to be 60. So we'll go back to our table here. So we're going to look in our within groups degrees of freedom column, and we're going to look for 60. So we'll have to scroll down until we get to about 60, and you're going to see it right here on the very next page, 60. And remember, we're still looking at 3 groups, so we're in that 3 groups column. And if we remember from our scenario, we have an alpha of 0.01. So that means that it looks like our critical value in this case is going to be 4.28. Now remember, the Q statistic is just like the T statistic. It is a normal distribution. So it's not a skewed distribution like the F distribution. It's centered at a Q equals 0. So that means our critical values are going to be in both tails. And so in this case, with the Q test, always, we're doing a 2-tailed Q test. So when I get this value of 4.28, that's a positive 4.28 and a negative 4.28 for our critical values. Now the distribution works the same as any other distribution. In the shaded regions, we would reject the null in comparing our 2 groups. So if I'm comparing neutral versus negative, my null hypothesis is that there's no difference between those 2 when it comes to caring for one's parents. So if I reject the null, I'm rejecting that there's no difference. And so that reject null will be in both the positive and negative direction. If we get a Q critical value that is between those 2, we're going to fail to reject the null. In other words, we're going to say it appears that there's no difference among our 2 groups. We fail to reject the null hypothesis. So let's go back to our spreadsheet here. I'm going to put our Q critical value. And we said it was positive and negative 4.28. So now I'm going to compare each of my Q statistics to that Q critical value. I went ahead and put up the distribution up there with our 3 different regions with our critical values. Let's take a look at our very first comparison. So our negative outlook versus neutral outlook, we get a value of, looks like negative 6.71. So negative 6.71 would fall someplace right about here in our reject the null region. If I look at negative versus positive, I get a negative 6.05. So again, that will also fall within our critical region, negative 6.05. We're going to reject the null hypothesis. And then finally, when we're comparing our neutral group versus the positive group, we get a Q statistic of 0.66. 0.66 falls right about here. So this is going to fall within our fail to reject the null hypothesis. And so that's going to be our statistical decision for each one of our comparisons within that post hoc test. So just notice essentially what we did was 3 additional hypothesis tests comparing each of our groups 2 at a time. Okay, so if we were to write that out, we would look at our Q statistic. Here we have a negative value. So that negative value is telling us that one group is less than another group. And that's how we want to word our response to this particular analysis. So all I have to do is go up here to the means and look at my negative outlook and see a mean of 5.17. And then look at my neutral outlook and see that I have a mean of 6.68. So comparing those means, it looks like those with a negative outlook are less likely to care for their parents than those with a neutral outlook. So when I'm writing this out, I would say I would reject the null hypothesis. It appears that people with a negative outlook on life are less likely to care for their parents than people with a neutral outlook on life. And that's how I'd write out my response. Now here I just abbreviated reject null with RN. You could type it out, reject the null hypothesis. That would be fine as well. Okay, so if we're looking at negative versus positive, you're going to notice that it's pretty much the same. We're still going to reject the null hypothesis. In fact, everything's going to be pretty much the same here, except instead of saying neutral outlook, we're going to say positive outlook. Again, it's still a negative number. If I go up and look at my means, I'll see the mean for positive outlook is higher than my mean for the negative outlook. So that means negative outlook is less likely. And so it appears that people with a negative outlook on life are less likely to care for their parents than people with a positive outlook on life. So that's our second comparison. Our statistical decision for our third comparison was going to be fail to reject the null hypothesis. Right, because remember our Q statistic of 0.66 did not exceed our critical values. It fell in the middle of our distribution. So we say here that it appears that there is no difference in people's likelihood to care for one's parents regardless if they have a neutral or positive outlook on life. So to summarize, we found with the Ftest that there was at least one difference among our groups. We rejected the null with the Ftest when we compared the F statistic to the F critical value. We then did our post hoc test to find out where that difference is. We knew there was at least one. And in this case, it looks like there were two differences, and those differences were between the negative outlook versus the neutral outlook, and then negative outlook versus the positive outlook. So it appears in both those conditions that if you have a negative outlook on life, you're less likely to care for your parents than you are if you have a neutral or positive outlook on life. And it doesn't look like there's any difference between neutral and positive. Any outlook on life is better than a negative outlook on life. And remember, with our effect size, we found it at the individual, not only at the group level as well. All right, so that is a between groups ANOVA with its corresponding effect size and post hoc tests. Don't forget to upload your spreadsheet and replace the file name with your name and submit below.